Okay, great. It's 11 o'clock. I'm going to go ahead and get started. I am recording this video, so if anybody wants to watch it afterwards, you can get with your rep. Your Insight Partners rep will make sure to get that to you. I'm going to put it up on YouTube, and I'll send everybody the link, and we'll go ahead and get that to you. So, okay, so welcome. This is the second webinar in our Psychrometric series. This is called Psychrometrics Beyond the Basics. And want to thank everyone again for joining us on the first one. It looks like we have a lot more people on this one, so that's always a good sign. And we hope everybody's staying safe out there and doing the best they can to get by and all this stuff. So these webinars are part of kind of an initiative that we're taking at Insight Partners to make sure during this time we could still bring you all, some quality content. We're hoping it's quality for you, and kind of keep connected to everybody. And this just seems like a good way to do it. So any topics you want to see, you can message me in the chat or get with your Insight rep and they could filter that to me, and we'll look at doing that. So if you missed the first video on Psychrometrics, we can get you a link to that. It's on our YouTube channel. Or you can connect with us on LinkedIn, Insight Partners on LinkedIn. All the stuff we do is posted there. And I'll ask you to connect with us at the end too if you want to sign up for the next webinar, which we'll be announcing. We'll be announcing there. So if you would, save your questions to the end of the webinar today. And you can ask the questions in the chat during the whole webinar, but then what I'll do is I'll stay afterwards. It's only 30 minutes, and I'll be glad to stay afterwards and answer any questions that I can. And if you're an engineer and you're looking for PDH credits, this does qualify for half PDH in North Carolina and South Carolina and Georgia. And we apologize to Florida. We're working on that. We'll get that qualified as soon as we can. Okay, so just a little bit about me. My name's Tony Mormino, graduate of College of Engineering, University of Florida, 97. Went to work for Trane in Jacksonville for 10 years as a sales engineer there. Also went to the graduate training program in La Crosse, Wisconsin, where we did 6 months of psychrometrics and learning about equipment, that kind of stuff, factory tours. Then I left there in 2007. I went to work and helped start and build a company called Innovative HVAC Sales with a couple of good friends of mine. They're still there running it. Left there in 2018. In Jacksonville, I was part owner. I was sales manager and sales engineer at that company. And now I work for Insight Partners, and I'm here in Asheville, North Carolina, which is where I'm broadcasting from. And I'm a sales engineer here, and I also handle some of the training and stuff like this you're watching. And a quick note, I forgot to mention at the beginning, I live up in the mountains, and everybody's home right now using their internet. So if by chance my internet goes down, I will continue this webinar. I'm recording it, and I'll just send everybody the link to it. I may have to shut off the video in the meantime. And if you would, let me know if you have trouble hearing me or seeing me in the chat. I greatly appreciate it. Okay, so the last webinar we talked about, it was a basic, how do you read a psychrometric chart? And we talked about the properties of air, building the chart, moving around the chart, psychrometric processes, and RH versus dew point. Okay, so we kind of got all that down on the first one. If you need a copy of that, let us know. We'll get you a copy of the recording of that one. So for today, we're going to move into air mixing. We're going to talk about sensible heat ratio, which is very important. We're going to look at calculating air quantity, as we call it, CFM in the business, cubic feet per minute. And then we're going to look at calculating the tons required in a refrigeration system. And we'll talk a little bit about full load versus part load, and see how systems react at part load. So that's the agenda for the day. And at the end, be glad to answer any questions you guys might have. So air mixing is the first segment here. So I understand the audio is cutting out really bad. Can someone else confirm that? I got a note that the audio is cutting in and out. Okay, sorry, whoever said that, maybe it's just on your end. Sorry about that. Okay, so to continue, and thanks for letting me know. So to continue, let's say we have a typical HVAC system here. We have 25% of outside air. We have a design day of 9578. We have return air, 72 degrees, 50%, and we're going to calculate the mixed air conditions and then kind of look at that on the psychrometric chart. Okay, so we use this mixed air temperature equation, which is outdoor air temperature times percent of OA plus return air temperature times percent of return air. In this case, the outdoor air percent is 25, return air is 75. So if we plug it into this equation, 95 times 0.25 plus 72 times 0.75, blah, blah, blah. So we get 78 degrees roughly. So we're going to round that up to 78 degrees dry bulb just to make things easy. Okay, let's go to our psychrometric chart. And we're going to plot our outside air conditions and our return air conditions. So 95 degree wet bulb, dry bulb. We go up to the 78 degree wet bulb line, 75, 6, 7, 78. We put a dot there, and that's our outside air point. So for the return air, it's 72 degrees. We go up to our 50% line, which is right here, 50% RH. Those are the two knowns. We put our plot there. And what we're going to do is go ahead and connect these lines. This is just the equation we just went through on the other page. We're going to connect these lines here, and then we're going to plot our mixed air dry bulb and get all the other points off of the psychrometric chart. So 78 degrees dry bulb, go up, hit this line, and that represents the mixed air temperature conditions. Now from that, we can pull all the other properties of that mixed state. So wet bulb temperature is 65. If we go over to the right, we can see the grains, humidity ratio in grains is, I'd say about 72. And the dew point is, let's see, 55, 56, 57, about 58. So now from doing this equation, plotting the outside air and return air, and then plotting the dry bulb, we can get all the other conditions of the mixed air. So now we can go back here and just fill this in. So 78 degree Fahrenheit dry bulb, 65 Fahrenheit wet bulb. Okay, so why is that important? We're going to see kind of later why that's important. Okay, now we're going to talk about the sensible heat ratio. And the SHR is really, really important when we're designing HVAC systems to make sure we can meet the design conditions or the design intent of the space. And the challenge we have as designers and manufacturers selecting equipment is the SHR always changes. So what happens on design day doesn't always happen on part load day. To understand this, let's first look at sensible versus latent heat. Okay, we have to understand those two. So when you're talking about sensible heat's the radiated heat kind of off of an object, like the sun hitting your hands, that's all sensible heat. It's completely independent of the moisture content of the air. If you walk by your stove and the burner's on and you put your hand over it, that's sensible heat. It's all radiated. So sun coming through your window, that's sensible heat. And there's all kinds of things in an office building or a home that generate sensible heat. I put some here. Computer, obviously, as a heat load. If you had a television in your conference room, printer, copier, people generate sensible heat and latent heat. We'll look at that in a minute. And then printer, I think I already mentioned that, but there's tons of stuff in a building that would generate sensible heat. As opposed to latent heat, which has to do with the moisture content of the air. So as we add moisture to the air, we're adding a latent heat component to the air. So it has to do also with the change of state. So the energy required to change from a vapor to a liquid has to do with the latent heat. So we think of latent heat, think about moisture. So if it's a cool rainy day and you're bringing in outside air, that's got a lot of water in it, that's adding latent heat to the space. People give off latent heat. If you got a coffee mug, coffee coming out of it's latent heat. If you got a sink in the bathroom, that's latent. That's going to be latent moisture added to the space. If you had a locker room with a shower, if you had a water feature, this is supposed to be a water feature, in your office building, like a fountain or something, that's adding a lot of latent load to the space. So as an example, if you looked at this area here, you have sensible heat coming through the window. You have a radiator in the back producing sensible heat. You have a cat that's giving off sensible heat, a living animal, and then some latent heat as well. If you look at this space is full of sensible and latent heat. Okay, you got sensible heat off the lights, the TV, the people, the camera, and then you've got latent heat. I'm sure I see one drink of water here, but I'm sure there's plenty more. And then all the people are giving off latent heat. And then there's a latent component with the ventilation air. So there's all kinds of stuff going on in this space here. So hopefully that gives you a little bit of an idea of the difference between latent and sensible heat. So it's expressed in BTUs per hour. Sensible and latent is expressed in BTUs per hour. And if you watch the first webinar, a BTU is short for British Thermal Unit. It's the amount of energy required to raise 1 pound of water 1 degree. And interesting factoid, even the British don't use the British Thermal Unit anymore. I think we're the only one left on there. So kind of funny little footnote. Okay, so when we're looking at the psychrometric chart and we're talking about sensible versus latent heat, what we're talking about is sensible heat has to do with moving from the left to the right. Okay, so dry bulb temperature has to do with sensible heat. So if you're moving from 95 down to 70, you're removing sensible heat. You're not doing any type of latent work. You're not adding any humidity or removing any humidity. If you move down on the psychrometric chart, you are removing humidity. You're moving latent heat, latent load. This one going from, 108 grains down to 32 grains of moisture in the air. So we were removing some moisture. We're not doing anything to the sensible heat of the space. So if we look at how cooling coils operate, typically we're removing sensible and latent heat depending on the application. Okay, so we're moving in this general direction. And the point is to remove the right ratio so that you can meet the design objectives in the space. So we're going to look at that here in a minute. So I like to think of the CFM like a sponge, okay? And it comes into the space and it has to be dry enough and cool enough to absorb the sensible and latent heat in the correct ratio so that the resultant temperature and humidity of the space is your design. So if you want 72 degrees and 50% RH in this space, the air needs to be cool enough and dry enough to absorb the heat load in the space to accomplish that. And there's, if you look at this space here, you've got windows here with sensible load, you've got people, latent load. Sure, there's a coffee mug there. So there's not much going on here, but there's some stuff there going on. So computers for latent load or for sensible load. So we're talking about removing sensible and latent heat. We gotta, like we said, we gotta remove it in the right ratio. So if we remove a lot of sensible heat and not enough moisture, the result is going to be a cooler and damper space. And if we remove a lot of moisture and not enough sensible heat, you're going to have a warmer and drier space. So it's important that we get the ratio right. So let's take an example of, let's look at that office space we just looked at. Let's pretend you ran a building load on it and it came out with your sensible heat, latent heat, and the total heat. So in this example, you've got 80,000 BTUs of sensible heat load on that space. The latent load's 20,000, which is a total of 100,000 BTUs per hour. So the SHR, the sensible heat ratio, is just the sensible heat divided by the total heat. So in this case, it would be 80,000 BTUs per hour divided by 100,000 BTUs per hour, which is an SHR of 0.8. So we go to our psychrometric chart and we plot the sensible heat ratio. And those numbers are located right here on this particular chart. Some charts are a little bit different. This has them right here. They go from 1.0, which would be a horizontal line, which would make sense because it's all sensible. And then it goes to 0.95, 0.85, 0.80, 0.7, and it goes all the way around here to 0.15. And typically in HVAC, you know, what we're dealing with HVAC industry is in this range, you know, maybe 0.6 to 0.9, something like that. Okay, so we're going to draw the 0.8 SHR. So what we do is we find this thing on the chart called an index point, which is located right here on this particular chart. We line that up with a 0.8 with our straight edge and we draw a line. So this represents the correct slope for a 0.8 SHR. Okay. Now let's, for example, say we had a space that was, the design conditions were 75 and 50% RH, 75 dry bulb, 50% RH, which is right here. Just happens to line up with the index point, which is why I chose this, because it's easy to demonstrate this. So what I'm trying to show here is that any temperature and wet bulb, any dry bulb, wet bulb ratio along this line, given the right CFM, will result in the correct intent. So anything along here for supplier to the space, as far as dry bulb and wet bulb relationship, will meet the design intent. Obviously, they will have different airflows, different CFM, and we'll look at that here in a minute. Okay, so let's look at an SHR of 0.6. And this is just an example to show you how to draw different SHR lines. And a design condition of 80 degrees dry bulb and 60 degrees, 60% RH. Okay, so we find our index point. We look for 0.6 over here, sensible heat ratios. We draw a straight edge. Okay, so now that represents a sensible heat ratio of 0.6. Design conditions of 80 degrees, 60% RH, so 80 degrees is here. 60% RH line is here. So go ahead and draw that line there. So what we want to know is what temperature dry bulb and wet bulb ratio do we need to provide to meet this design intent? So what we do is we take this SHR line and we move it up to our design point right here. So what we're doing with the index point and this number over here is we're just getting the slope, basically. We can move that slope up and down the chart, figure out how to meet different design intents. So like before, anything that falls in this line will have the correct ratio of temperature and humidity to absorb what's in the space to meet the design intent. But they will all have different CFM. So we'll look at that here in a second. All right, so calculating air quantity is the next section. We're talking about air quantity. We're talking about CFM, cubic feet per minute, if you're new to the industry. So the step one is to calculate the SHR, which we've already done. In this case, it's 80,000 over 100,000. So it would be SHR of 0.8. In step two, we're going to plot the makeup air, the mixed air temperature, outdoor air temperature, and room temperature on the psych chart. We've already calculated the mixed air temperature of 78. So let's go to the psych chart and plot these things. Okay, so our outside air, 9578. Our return air, which is our design conditions, is 72, 50%. Connect these lines, plot your mixed air temperature right here. Then we know it's a wet bulb of 65, so we can go over here. Okay, so that was just an example of plotting these things on the chart. We kind of already done that, but wanted to go through it again. So we're going to label these A for return, B for outside air, and C for our mixed air temperature. Okay, now we're going to draw our SHR line, 0.8, find the index point, match it up with 0.8 over here, draw the slope, move the line down to where we want the space conditions to be, which is point A. And now what we're trying to do here is figure out what our supply air temperature needs to be, because we need to have that to calculate our CFM. So what's happening here is I'm connecting point C, which is our mixed air temperature. It goes through a cooling coil, which removes sensible and latent heat, and intersects our SHR down here, okay? Now, some charts have coil curves on them. That's a whole other discussion, because the actual slope looks something like this, comes straight, and then starts dropping like that. But we're just going to make it simple. We're going to connect the 2 points here. So point D, which happens to be 49 dry, 48.5 wet, is our leaving air temperature we're going to pick to calculate our CFM. Okay, step 4 is to calculate the supply air CFM. And this equation, if you're new to the industry, is a big one. Might be one you want to write down and keep on your side. Most psych charts, and if you need a psychrometric chart, get with your Insight Partners rep. We have them. And these equations are on the charts as well. So supply air flow equals sensible heat gain over 1.085 times room dry bulb minus supply air dry bulb, or supply dry bulb. So we go ahead and plug in what we know now, which is 80,000 BTUs per hour divided by 1.085 times 72 minus 49, which is the temperature we just got from the chart. That's why we had to get that supply air temperature. And that equals 3,200 CFM. Okay. So if we take our HVAC system we looked at in the beginning, we have 3,200 CFM of total air, 78 degree dry, 65 wet, 25% outdoor air, which is 800, 95 dry, 78 wet, 2,400 CFM of return air at 72, 50% RH. And our resultant supply air is 3,200 CFM at 49, 48.5. Okay, so we calculated the leaving air, we found the leaving air temperature, calculated the mixed air temperature, found the leaving air temperature, calculated the CFM. Okay, the next thing we're gonna look at is calculating the tons of refrigeration required. Take a sip of my coffee. So if you're new to the business, tons here is not a weight. What we're talking about is a unit of energy. It's actually 12,000 BTUs. And I looked up the history of that. It actually came to be about when, a long time ago, they used to harvest ice from cold areas and they'd bring them to warm areas. So when refrigeration came around, they needed a unit of measure to talk about, compare the ices. So a ton in air conditioning is actually the BTUs required to melt 1 ton of ice. Okay, I will do that. Good point. It was suggested that I discuss thank you for reminding me. I forgot about that, to mention that. So 1.085 is not a constant, by the way. It has to do with the density of the air. And if you want some more information on that, you can stick around afterwards. We'll go through what I know about it, but it does change with density. Okay, so at higher altitudes, the 1.085 will change. Thanks for bringing that up. I appreciate it. Okay, so a ton is 12,000 BTUs. It's the amount of energy required to melt a ton of ice, basically. So here's the equation for tons of refrigeration. This is also one of those biggies. If you're in the industry, you might want to write this down. It's also on our psychrometric chart. So tons in BTUs per hour equals 4.5. And this, again, is not a constant. Okay, this will change with the density of the air. Times supply airflow, which is 3,200 in this case, times delta H, which is a new term in this webinar called enthalpy. We talked about that before, but we're going to look at that a little bit in a minute. And the enthalpy has to do with the total energy in the air. So if we're calculating the tons of refrigeration needed, we need to know the sensible plus the latent heat, and that's what enthalpy is. Okay, it's total heat energy of 1 pound of of air. And where we find that on the psychrometric chart is right here. There's the enthalpy lines here. Starts at, I believe, 10, goes up to 50, and even comes over here. And then we have an enthalpy line here. Starts at 5, 10, 15, 20, 25, 30. So the way you use the enthalpy on the chart is you line up two numbers, let's say 30, for example. You connect them with a straight edge, and that's your enthalpy line for 30. So what we're going to do is line up point C. We're going to get the enthalpy of point C, which is 29.8. That air is going to go through our cooling coil. And we'll get the enthalpy of point D, which is 19.5. So this delta H is what we will use in the calculation of the tons of refrigeration. And if you think about it, it's your mixed air temperature going through your cooling coil, your leaving air temperature there, so that makes sense. So if we plug this in, 4.5 times 3,200 times delta H is 148,000 and some change BTUs per hour, which is about 12.36 tons. So if you divide that by 12,000, you get your tons. So 12-ton-ish system. And just to note, you can also break this up into sensible and latent components. If you draw the enthalpy line through our room conditions, this delta H can be used for the latent load, and this delta H can be used for the sensible load. And you would do that by plugging in the same information that we did up here. We're not going to go through that right now, kind of run out of time. So, okay, full load, part load. Got a few minutes left here, so I'm going to go pretty quick. So full load conditions are easy to design for and easy to hold the space temperature and humidity. It's really the part load that's the challenge in the HVAC industry. So we'll take a part load SHR of 0.7. Let's say it's a cool, cloudy day in October. Okay, we had 80,000 BTUs of sensible heat. Now we have 47,000 BTUs. So we'll leave the latent the same. So 47,000 plus the 20 latent we had is 67,000. So that results in a 0.7 SHR. So here's the complete system at full load we talked about earlier with a 0.8 SHR. So let's go ahead and draw our 0.7 SHR line. Technically, you would line up the index point with 0.7, draw it out, and then move it, but I just put it on here. I already did all that part of the work. So, okay, so here's our new sensible heat ratio. So what we have to do to meet the design conditions now is either change the discharge air temperature or change the CFM. Let's say we have a constant volume fan coil unit with a modulating valve, okay? So that's easy to kind of visualize how we could change the leaving air temperature. So what does the leaving air temperature of that fan coil unit need to be given this SHR to achieve the design conditions of the space? What we do is we just take the equation we used before, the sensible heat equation. This time we use 47,000 BTUs for the sensible, and we know the constant here. Well, it's not a constant, it's constant in this case for this webinar. And then we take our 72-degree design temperature of the room minus supply dry bulb, which is our X, basically. So if we solve for the supply dry bulb, that's 58.4 degrees, okay? If we plot the 58.4 on the chart, what we do is we run this line up to this intersect point, which is our cooling coil line. Excuse me. And then we take our SHR line of 0.7 and we run it up to meet the new leaving air temperature, okay? So the new leaving air temperature is here, 58.4. It's going to follow this slope, absorb the heat and moisture in the space along this line, and it's going to result in this temperature right here, which is our design temperature of 72. Now, the important thing to note here, and which is why I put this demo on here, is the humidity is not the same as it was before. So at part load, it's pretty easy to meet the design intent as far as dry bulb temperature. it's not so easy to meet the design intent when it comes to humidity. So we were at 50% RH, and now we're at 60% RH. And this example is pretty forgiving. You know, if you have an auditorium or cafeteria where you've got a lot of people and you've got huge variable loads, the SHR could swing pretty high, and you can get into all kinds of problems at part load if you don't have the right systems in place to manage that. So, and that's A prime. I just forgot to put it up there. Okay, we are out of time. I was going to go through this dehumidification sequence. If anybody wants to stick around, I'll go through it. I'm going to shoot to the end here, talk to you a little bit about what's coming up next. Let me do this. All right, what's next? So we're probably going to have another webinar in 2 weeks, maybe 3 weeks. We're not sure yet. And I'm not sure what the topic is going to be yet. We have a couple in mind. So to get connected to us, to sign up for the next webinar, I'm going to chat you guys this link here. Connect with us on LinkedIn. All of our webinars that we've done in the past, and all the webinars that we're doing in the future, we post on our LinkedIn Insight Partners page. So I'm going to chat. Let's see here. Chat this link to everybody, or you could just go there if you want to. Okay, where's my chat? Ah, there it is. Okay. Paste. Okay, just sent it. So join us on LinkedIn. Come get connected to us. That's where we put all of our current stuff on there. Check us out for the next one. And we'll also be emailing everybody. If you're an Insight Partners customer, from your rep, you can get the sign-up sheets you need for your PDH, and you could also get the link to the last video, last webinar, and the link to this video recording as well. So we thank you all very much for joining us. It is a little bit past 11:30. I'll end it now and be glad to sit here and answer any questions. And I ask that everybody please stay safe, and thank you very much.